Okay, welcome everyone. For those of you all undergrads in physics, I'm Dr. Malcolm from Geography and Environment. It's great to have all of you out here on such a kind of crappy day at the end of the week. Great for you to come out and listen to Dr. Fugleberg. Okay, so Dr. Fugleberg got his BSc in physics from the University of Saskatchewan, and then he went to UBC for a master's and PhD. He had an NSERC postdoc after that at Brookhaven National Laboratory, Long Island, New York. And then he came to BU as a postdoc with Dr. Carrington. So I'll walk in back with Dr. Carrington in the fall of 2002. And when she was named research chair, he was hired in a term position. And as he says, he's been here happily ever since. So over to you. Thank you.
Thanks for the opportunity to talk. I'm going to be talking today about particle production from gravitational waves, and just want to acknowledge that some of the basic research that led to this was done by a honors thesis student of mine a couple of years ago, Jesse. So the outline is, first I'm going to introduce the concept of gravitational waves. We'll talk about the idea of space-time curvature and show you a bunch of little videos of ways you can visualize what's happening in the gravitational waves, talk about how they detect gravitational waves. Then I have to do a really brief introduction of the idea of where particles come out of field theory, talk about electromagnetic waves and photons, and then introduce the concept of matter fields and how particles are represented in field theory. And then I'll talk about the actual research with the interaction of gravitational waves and matter fields, which involves signing the Klein-Gordon differential equation, and then get back to the idea of how this result connects to the idea of particles, and then very briefly talk about the physical implications at the end. So 1915, Einstein published a general theory of relativity. The basic idea is that matter curves space, and then particles moving in space follow what are straight paths in the space. They look curved to us, but because of the curvature, they're actually straight lines. And that explains the force of gravity. So here I've got this little simulation, and basically, instead of making this object, which might be a star or something like that, bigger and bigger, then you can't see the dip in the curvature. Basically, I'm changing the density. So when it's flat, when the density is 0, you basically think of that as a ball of basically nothing, like gas. And as I turn up the density, I'm increasing the density so that it becomes, a star, or a neutron star, or even a black hole. And so with the largest density, you have the largest mass, and you can see that the space is curved. I'm not going to get into the details of how particles react to the curved space, but the idea is that in addition to the idea of matter curving space, Einstein also predicted the idea of gravitational waves, which are traveling waves of curvature in space-time. And so for a wave traveling in say, if this is the z direction, they're traveling in this direction, what you have is you have compression and expansion of distances in the directions that are perpendicular to that. So if it's traveling in the z direction, you basically have distances in the x and y directions that are shrinking and expanding and shrinking and expanding. Now, it's important to say that particles, things in the space-time, are staying at the same coordinates. They're not really moving. It's the space itself which is shrinking and expanding. So this is a little video here, and it showing this idea. So basically, again, if the gravitational wave is going in this direction out of the board at you, if you were sitting there, what you would see is these particles, these little red particles that are staying at the same position, but the space between them gets stretched and contracted. And for a gravitational wave, what you'll see is that it stretches in the x direction and contracts in the y direction, and then it stretches in the y direction and contracts in the x direction. This is a little bit easier to see if you have a ring of particles at fixed positions. If this gravitational wave is coming out of the screen at you, and you have these ring of particles, basically they look like they're moving. They're really staying at the same place, but the distances between them are being stretched and compressed. So that's what you'd see of a gravitational wave coming out of the board at you. Trying to show this in a three-dimensional way is a little bit hard. So this is, if you had like a cylindrical tube, a flexible cylindrical tube, this is basically what a gravitational wave would look like. You can see it's compressing in one direction and stretching in the other and changing. And it's the compression waves are moving, traveling in the Z direction. For the biologists out there, I always find that to be looks very peristaltic. So where do gravitational waves come from? The main sources are binary systems. So you have a bound system of two stars and they're orbiting one another, or a common center of gravity. And because you have that system, they're actually emitting gravitational waves. So if you have a bound stable system, you'll have them emitting gravitational waves as long as they're orbiting one another. Of the gravitational waves that have been detected, it's actually a much more drastic situation where you have a massive stars, actually very dense stars like neutron stars and or black holes, and they've lost a lot of energy due to the radiation of gravitational waves, and they're spiraling in and then colliding. It's called a binary merger, and those are the much more violent processes that produce the gravitational waves that we've seen. There are remnants, predicted to be remnant waves from the Big Bang, which we don't have the capability to detect right now. So the first direct observation was in 2015, 100 years after Einstein's, well, actually 99 years after Einstein first predicted them. Gravitational wave source 150914. This was BP Abbott and then a whole bunch of names from the collaboration listed after him. And there have been more than 90 candidates since observed. So this is just a little video that comes from the LIGO website. So you have these two stars, they're orbiting one another, and they're sending out these gravitational waves. So why did it take so long for 99 years for them to detect the first gravitational wave? The amplitude of the gravitational waves is the relative expansion. How much do they stretch the distances in the x direction relative to the original x size? So what is the change in the size of an object in the x direction relative to its natural size? And similarly, what is the change in the y direction, delta y, relative to the natural size y? The largest amplitude gravitational waves ever detected have a strain. This is, the ratio of the change in length to the length is what's called the strain. The largest amplitude gravitational wave had a strain of about 10 to the minus 21. Very, very, very tiny effects. And the amplitude is very small, partly because of the predictions of general relativity. Even near the source, the gravitational waves are not that big. And they're very, very long distance away from us. And because the waves are spreading out over a sphere expanding from the source, that energy has to be distributed over a larger and larger sphere, which means the amplitude of these waves has to decrease as it travels. So these are very, very small. So direct detection of gravitational waves is really an amazing achievement. So this is a collaboration of collaborations. LIGO is one of the big collaborations. They have a site in Hanford, Washington State, and a site in Livingston, Louisiana. And they're since now collaborating all together with the Virgo collaboration. We have their site near Pisa in Italy, and Cagra, which is in Japan. And this is an artist rendition because it's actually 200 meters underground. So you basically have these really, really long arms where you have a vacuum. And what happens is they're sending laser beams down those arms and then recombining them. So the arms of LIGO are about 4 kilometers long in each direction. In Virgo and Cagra, they're about 3 kilometers. So what's happening is they have what's called an interferometer. Oops. And what happens is they have a single laser beam. And a laser beam is coherent light, which means it's all the same frequency. And all of the little bits of it have the same phase. They're all increasing and decreasing exactly in lockstep with one another. And they send this laser beam, they shoot it out, and this is a beam splitter, which is basically a half reflective mirror that transmits some light and reflects some light. And it divides the beam in two. So some of it goes down the forward arm, and some of it gets reflected around the perpendicular arm, and then go 4 kilometers down and 4 kilometers back, 4 kilometers down, 4 kilometers back. And again, this is partially reflected, partially transmitting. So some of the beam that came from this perpendicular arm is transmitted, and some of the beam that's coming from the forward arm is reflected. And those two beams are now recombined in this beam here. And the point is that those lasers, if they travel exactly the same distance, they're going to be still in phase with one another, which means they're going to be having the peaks and the troughs in the same position, and they're going to add, and you're going to have a bright spot. If there's any change in the distance, then they're going to be out of phase, and you're going to have a dim spot. So this is my animation here. So you have the beam coming in from the perpendicular direction, and the beam coming in from the reflected beams that are coming back after having gone 4 kilometers out and back. And they're hitting this mirror, and you can see that these two beams, if they've traveled the same distance, then they're hitting the peak at the same time, and they're hitting the trough at the same time, and then they add. So you get a beam out here. The combined beam is bigger than either of those two because they're adding construction. If they're a little bit out of phase, if they've traveled a little bit of a different distance, they're not in phase, and they're actually now having destructive interference. So basically they're interfering with one another, and the beam that's coming out, the combined beam, has less amplitude than those two recombined beams, or two beams from the different arms. And then if they're completely exactly out of phase with one another, if one is hitting a peak when the other is hitting a trough, then they exactly cancel out, and you get no beam. There's no light. So what happens, this is a video from the LIGO website, which basically has, you've got the laser source, the mirror, the beam splitter, and then you've got the two mirrors at the end of the arms, and then you've got the light detector here. So it shoots the laser, it gets split up, comes back, recombines, and then you observe what's happening here. And you can see as these ends of the move, then you get a brightening and dimming of the light that's hitting the detector. Because as we said, you've got a light going down to the 4 kilometers being reflected back, and then they're recombining, and they're being detected here. And when these, because of the gravitational wave, if these distances change because of the movement, that's going to change whether they're constructively giving you a bright spot or destructively giving you a dim spot. So that's how they measure the change in these lengths of these really long arms where the laser beams are going through these cavities. And this is, I'm basically repeating a previous slide because it's so important. We said that the gravitational wave, they're measuring changes in distances about 10 to the minus 21. So if you're looking at the change in the length of these 4 kilometers long arms, that's basically measuring a change in distance of about a millionth of the width of a proton. Tiny. If you look at the LIGO website, they say that's equivalent to measuring the distance to the nearest star 4.2 light years away to an accuracy within the width of a human hair. Really impressive. And again, this amplitude is very small because of GR itself and because of the large distance between sources. So this is really amazing. But because it's so such a weak signal, oh, I left it over there. Before they were detected, and even since then, people have said, well, are there other ways we can look at the effects of gravitational waves? And one of the ways was the first indirect evidence. Basically, when the binary system is these stars are orbiting one another, they're emitting gravitational waves, so they're emitting energy. So they're losing energy, which means they're spiraling in. And in 1974, Taylor and Hulse detected a binary system that had a pulsar in it that gave them a very accurate plot to measure the periods of this binary system. And from that, they calculated, the paper was published in 1982, they calculated the loss of the orbital decay of this binary system exactly matched what the predictions of energy loss due to emission of gravitational waves. They won it in 1990. Hulse and Taylor won the Nobel Prize in 1993. But that's one way. Another way you might say, okay, you've got the space-time that, doing the funky chicken. How does that affect the other particles and physical fields that are moving in this space-time? Propagation is a fancy field theory word for moving. So now I have to give you a really brief introduction to the concept of quantum fields. Some of you may know that light is an electromagnetic wave, which means it's a traveling oscillation of electric and magnetic fields. So you have an electromagnetic wave going along this direction, along the direction of this rectangular cylinder, and you have an electric field which is oscillating in the vertical direction, and you have a magnetic field which is oscillating in the horizontal direction. And the oscillation of the electric field causes the oscillation of the magnetic field and vice versa. So it's a stable thing where each one causes the other. So that's what light is really. And the oscillations you can see of the fields are perpendicular to one another and perpendicular to the direction of travel. So that's what light is. But you might have heard of photons. So photons are basically required to consider the behavior of light at microscopic levels. And they're localized. They're basically like particles of light. So in a very rough way, you can sort of consider a particle of light. This is very rough. Don't take this too seriously, but you can consider the idea of a wave packet where you have oscillating electric and magnetic field, but they're only oscillating in a very brief space. So there's oscillation of these fields, but the total oscillation is contained within a smaller region. That's what's called a wave packet. So in a very rough way, you can think of a photon as a localized excitation of electric and magnetic fields. What about matter particles, like electrons and protons and all the matter? Electric and magnetic fields are force fields, which means at each point in space, you have a little vector, a magnitude and a direction, which basically would tell you what the force of the charged particle would be at each. So at each point in space, you have a magnitude and direction. And if there was a particle there with charge on it, it would move, it was a certain acceleration because of that force. So that's what electric and magnetic fields are. So that's kind of easy to picture, relatively. Matter particles also have fields associated with them. It's a little bit more abstract because at each point in space, rather than having a force, you have a field which tells you how likely am I to observe a particle at that place. If I was to take a detector and put it there and try to detect a particle, how likely am I to actually detect a particle? And the size of that field is basically telling you the probability that you'll see a particle. And that probability is determined by this function phi of x, which we call a wave function. So the idea here is for particles of matter, I'm going to use an electron field, just it's a particle that most people have heard about. And you can think of an electron as a localized excitation of this electron field. Locally, if I look here, there's no chance of seeing electrons. If I look here, there is a chance of seeing electrons. So again, this is a very rough description. It's basically you have this field which is kind of abstract, and a particle is a localized excitation of it. But just like we said, light is an electromagnetic wave, and we can think of photons as being local excitations. You can think of there being a wave, a standing wave of an electron field. We don't just have to have just these localized electrons. We can have a wave of the electron. So this is just like a wave on a string or a traveling wave. So the question that we're asking is, what effect do gravitational field waves have on the propagation of quantum fields? If we were to look at particles, electrons, and that are coming from space or have a detector out in orbit, can we look at that data and detect the effect of the gravitational wave? If there is an interaction between the gravitational wave and these particles, does this cause the gravitational wave to lose energy? So could you detect that type of signal? So this is a very simple wave equation. It's a wave equation for waves on a string. So basically, I'm showing you the section of a string. I'm not showing you the ends because I don't want to show you a standing wave. And somebody is moving this string up and down, creating a traveling wave, which is going along the string. And y is the displacement in the vertical direction of the string, and x is the position along the string. And the wave equation is this differential equation. These are derivatives. The fact that there are these funny d's and not the regular d's is because this function, it's basically because the function depends on two variables. So you have to make your d's, your derivative d's, curly rather than straight. It's not that important. They're derivatives. And this basically says that this is the derivative with respect to time. So this is the position, the first derivative of the velocity. The second derivative of so this is the acceleration of a point in the vertical direction. So again, this is the string. Each part of the string is just staying in one place. It's just moving up and down. The wave is traveling, but the pieces of the string are just moving up and down as the wave goes by. So this is the acceleration of the string in the vertical direction. And this is the second derivative. The first derivative with respect to position is the slope. The second derivative is the curvature. So this basically says that the acceleration of any point in the string depends on how curved that string is at that point. I know, I wish I could stop it. So if you have a point and that's at this intersection point, it's basically a straight line as it goes through the axis. So there's no acceleration. At the points here, there's more curvature, which means it was going up and now it's starting to go down. So this just says the acceleration in the y direction depends on how curved the string is. And the v out front is just the speed at which the wave is moving. So that's basically, you look for a solution to that to tell you how the wave is moving. And we can subtract, we can take this expression, move this onto that side, and we can choose our time and space unit so that the speed is equal to 1. People in general do that a lot. They say, okay, I'm just going to call that 1. And so you get, this is basically the differential equation. So solving this equation means finding a function that has such that the second time derivative minus the second space derivative equals 0. It's time to find the function. Okay, so that's a very simple wave, but we want to look at waves in space-time. So rather than just having 2 derivatives, we're going to have 4 derivatives. You have the time derivative that we had before. You have this now, but now you have 3 derivatives because it's now not just going in one direction; it's going in some arbitrary direction. And this phi, this is the wave function that tells you how likely am I to see a particle there if I look. So this is called the wave equation in 4 dimensions. And you can actually solve this, find the function that satisfies this. This is a wave traveling in an arbitrary direction. Now, first off, this exponential doesn't look like a wave. But I'll just tell you, for those of you who don't know, e to the ikx, a complex exponential, has a cosine piece and a sine piece. And don't worry about the complex parts of it. Just say, if I see that, I know that it's oscillating like a sinusoidal wave. It has 2 different pieces, but that's not important. It's oscillating. And it depends, you have, it's moving in some arbitrary direction. It's going to have a wavelength in each of the 3 directions and a frequency at which it's moving up and down. Except when I say moving up and down, I'm not considering anything moving. This is just how that field is changing from point to point. Okay, so now I'm not satisfied with that. It's this is in terms of the usual X, Y, Z directions, it's useful to change the coordinates that you use. You can use a different coordinate by basically combining the time and space. In relativity, time and space mix. So I'm going to define a new coordinate that's a mixture of time and space. And it turns out if you have any function, the only thing to really take away from this is if you have any function of u, it's going to be traveling along this. This is again in relativity where you take the speed of light to be equal to 1. You choose your coordinates, your distance measurements, so that the speed of light is equal to 1. Anything slower than 1 is moving, any speed less than 1 is moving slower than the speed of light. So this, if it's a function of this combination, then it's moving in the forward direction, in the positive z direction at the speed of light. If it's a function of this variable, it's moving in the negative z direction at the speed of light. And just one thing here is that you can invert these and say, well, what is z in terms of these new coordinates? That's what z looks like. And why is it called light cone? Because if you expand it to 2 dimensions, it actually looks like a cone. I can't expand it to fully 3 spatial dimensions because I don't have 4 dimensions to plot it with. So that's why, that's only thing is, that's why they call it light cone coordinates. That's all. But if you use these new variables, this differential equation, which I'm trying to solve, becomes this. You still have the second derivative for space with the 2 spatial coordinates, but then you've got this other, it's just rewriting the differential equation. I'm solving a differential equation. That's the main point. But this is just, it's still, there's no curvature. Space-time is flat, but I'm just using a different set of coordinates. Now let's put curvature in. This, that's the equation that the wave equation is called the Klein-Gordon equation. That's the differential equation I'm trying to solve. So the important thing to realize is you're trying to solve a function of 4 different variables. You've got derivatives. So you're looking for the function such that this whole mess of stuff is equal to 0. It's complex, it's difficult, but there's some key things to notice here is that this term here, that is, well, we said that v minus u over 2 is equal to z. So this is 1 over z, 2 over this, that's 1 over z. So that's something that's decaying with distance. If you go further and further away, 1 over z gets smaller and smaller. But then you've got an h. So this term here, this is really the amplitude of the gravitational wave. This h is the amplitude it had when it was, near the source, and it's decreasing because it's spreading out. The energy is being spread out over a spherical surface, and the amplitude has to go. So this is the gravitational wave. That's the gravitational wave, and that's how it's affecting it. But you've got this all these other pieces, but they're all just, they're all the effect of the gravitational wave. So I've got this ugly looking differential equation. But if there was no gravitational wave, this h should be 0. That's the initial amplitude of it. So if there's no gravitational wave, this is 0, which means this is 1, this is 1, these 2 are 0, this is 1. These 2 go away, these 2 go away. And basically you can convince yourself that if h is equal to 0, you just get back. You get back to flat space. So the most important thing to realize is that these are the effects of the gravitational wave. And I'm trying to solve that ugly, horrible differential equation. One of the ways you can solve a differential equation is you can guess the form of the solution and then plug it into the differential equations and then try to make everything work out to give you 0. This is the assumed form of the solution. If h was equal to 0, you just have that, which would be equivalent to that exponential I showed you about 4 slides ago. I'm not going to get into it's ugly, it's horrible. It's something you can't just look at it and understand what it means. One thing to notice though is that you've got an h on top and you've got the v minus. So this is really, Each term is a sort of different powers of h over z. This is a small quantity that's getting smaller and smaller. You assume this form of the solution, you plug it into that differential equation, and then you try to solve for these coefficients. And if you do that, you get this mess. Again, it's really hard for you to, but that's basically what we're doing. We're taking the assumed form of the differential equation, a solution, we're plugging it into the differential equation. Then we're going to solve and try to make all these terms equal zero. And that's what we get. So that's basically what we did. But you say, okay, wait a minute. What does this have to do with particles? How do I look at that mess and understand it? Well, it turns out if you calculate you take that solution that we just flashed there, and you calculate this expression. You take the complex conjugate of it, you take the derivative, smash these things all together. This is something that's called the current, which is related to how many, it's not electric current, it's how many particles are passing a position with respect to time. And then you can also look at, I want to look at the cumulative effect. I'm going to integrate over one cycle of the gravitational wave. So I'm going to basically integrate over time through one complete cycle of gravitational wave and see what comes out. This notation just means the average particle current over the waveform. So the thing to notice here is if there's no gravitational wave, h is equal to 0, this is gone. So without the gravitational wave in flat space, this would be your current, related to the number of particles that you would see in flat space. So the wave is just, the wave of particles is just going along in flat space, that's what you'd see. But if that same wave is now traveling through a space-time that's doing this, you have this expression, because here you can see that's related to the amplitude of the gravitational wave, how much it's stretching. And therefore, this is the change in current that's caused by the gravitational wave. It's related to the frequency. This F is the frequency of the oscillation of the matter wave, the electron wave, or whatever particle it is. F sub g, that's the oscillation of the gravitation. And you can see it turns out that the frequencies of gravitational waves that are produced are very small compared to the frequencies of the matter fields that we see. So this is going to be an addition. So this is basically saying the effect of the gravitational wave is to increase the number of particles I see coming at me. And the physical implications of this are that you're going to have, if you have a detector that's looking for electrons or whatever out there in space or even on Earth, you're going to see that the density of these particles is oscillating for some reason. And it's oscillating because of the effect of the gravitational wave that's doing that. It's propagating through space. And the results we got for that are consistent with the previous results, where they only considered plain gravitational waves, which basically they didn't take into account the fact that this gravitational wave had to decay in amplitude and distance, which should have been a really good approximation. And I won't go into details. It turns out that I gave this project to an honors thesis student, thinking, oh, it's going to be close to that result. It's not going to be really that interesting, but you know what they're doing, they know how to do it, and they know what result they're going to get. And lo and behold, they did it, and it wasn't working. Something funny was happening. And it turns out that there was something interesting there that I don't really have. I'll mention it at the end, but I won't go into it in detail. So the gravitational wave will cause an oscillation in the number of particles that you just see around you in space. But there's also a cumulative effect. It seems like not only does it cause them to oscillate, it actually causes an increase in the number of particles. So basically, this gravitational wave goes for a really, really long distance, and you see a little bit more particles moving in that direction than you would expect normally. It's a small effect, but it's something that could be observable. And that is also consistent with different previous results from a different set of authors who did things differently than those authors. As long as the gravitational waves and the particle waves are moving in different directions. The other thing that we found is that these authors here, the two, they believe, based on their results, that if you had a gravitational wave moving through a vacuum, it would just produce particles. It would just create particles out of nothing. And they had their reasons for thinking it that way. We did the analysis and we checked that in a little different way. And then we said, no, that doesn't happen. You won't have a gravitational wave just producing particles out of nothing. There has to be some particles that were there to begin with. So if you've heard about cosmic background radiation, the entire universe is permeated with microwave radiation that's left over from the Big Bang. It used to be high energy and low frequency, but it's been stretched out through the expansion of the universe, and it's now microwave radiation. So the point we're saying is that you could have these gravitational waves interacting with any cosmic background field and producing more particles than you'd expect if there wasn't gravitation. And then, yeah, so the thing that I'm not going to go into is that we found, I gave this thesis project to an honors thesis student thinking the fairly well-defined problem. We know kind of what we're going to get. We're just going to add in the fact that it's decaying in amplitude. It's spreading out and the amplitude is getting smaller. I don't expect that to have a big effect. But it turns out that it does have a significant effect when you're considering particle waves that are moving in exactly the same direction as the gravitational waves, what we would call collinear waves. If these two different waves are moving in the same direction, the form of the solution is much different than the previous result for plane waves. So the basic idea here is there seems to be an observable effect, which you can look for in terms of how particles moving in a cosmic background radiation, the fact that if you have a gravitational wave moving through that cosmic background, they're going to produce more particles, and there's a signal that you could possibly look for. So that's basically it. One thing is that we basically considered a very long life gravitational wave, which would be coming from these basically fairly stable orbiting binary systems that weren't colliding with one another. And therefore there was no time dependence. But all of the gravitational wave signals we've seen so far come from this very violent collision, a merger of a neutron star and a black hole or two black holes, where they spiral in and hit each other. And that has a very rapid time dependence. So it would be nice if we could do the same thing and consider not just the spatial dependence, but also the time dependence. We'd also like to do it. This was actually for a type of field that we don't really see in our current universe, but the extension to electrons and electromagnetic radiation is doable, and we'd like to do that. And do some other things in terms of modeling the background fields and modeling what the actual form of the gravitational radiation is. So hopefully I was able to present at least part of that where you could sort of follow what the basic ideas was, and thanks for your time.
Very much, Dr. Fugleberg. I think for those online, I'm going to take questions from the classroom first, and then we'll look for questions online. So does anyone have a question? Yes, you did. Yes, you got it across. Oh, we got one in the back. Go ahead. We don't have a microphone to bring around this time, so just.
Well, I was commenting you on your presentation with spike out. I'm aware in the elementary physics that the photon attraction that exists between two bodies, okay, that is product of the forces, and also there is impact of the square of these types of continuum. I want to ask, how the study of particles and the production, from the field unit contribute our understanding of the black holes. Because if you look at the black holes, look at what happens, the first thing to be a kind of the particles, and even the light. Okay, it's not light, which is 3.0 times the power of 8 without. So the speed seems to be so high. How do this study actually, the production of the gravitational field contribute to understanding of the black holes and the
Okay, thanks. So basically, if they didn't hear at home, the question was, how does this idea of this interaction contribute to our knowledge of black holes?
Yeah.
Basically. So directly, anything we can study about the theory of gravity is important. And I'll just say that gravitational waves are actually a really useful tool. Now that we can actually detect them, you have the possibility of gravitational wave astronomy, where people can look at what they see in terms of visible light, and also look at gravitational waves and try to connect those and develop a better understanding of the theory of gravity. When you're like I said, one of the biggest sources of gravitational waves consists of large masses that are spiraling. So you have a number of the candidate gravitational waves that have been detected are probably mergers of black holes. So if you study the gravitational waves of coming off this merger of black holes, then you should be able to learn something about the process of merger of black holes. And that could tell us something about the nature of event horizons and things like that. I can't say anything more specific than that. I mean, any way that we can use to study black holes in the mergers could help us understand black holes a little bit better. Thanks for your question.
We do have a question that popped up online from Keith. Do gravitational waves differ in any way other than perhaps magnitude based on different sources? If so, what are the implications for this research? Oh, I'll get it. You can read it.
Well, the main difference is that they're a difference in nature. This is the other waves that we've looked at are waves that are propagating in space-time. This is the wave that's actually consisting of space-time. The space-time itself is the thing that's waving. So as I said, because it's different, it also can penetrate. Okay, basically, when you have the Big Bang, the universe was, came out of the Big Bang and expanded. And it was a long time before light could actually separate from the particles. So the universe was actually basically opaque for a very long time after the Big Bang. And then at some very late time, the energy cooled enough that basically you could get atoms forming, you could get particles forming, and the matter and the light decouple from one another. And the light that we see is coming from that, what we call the surface of last scattering. So when we look with light, visual astronomy, even radio waves, we can't see any earlier than that surface of last scattering. Whereas with gravitational waves, we could actually penetrate beyond that surface of last scattering. So we could use that to study the Big Bang much closer to the origin of the universe. I hope that answers your question.
Any other questions for Dr. Fugleberg?
We're talking about the trying to measure distances and kind of
Sorry, you mean the period of the oscillation or the wave of the laser?
the period of the oscillation.
Oh, okay. So the current LIGO collaboration, the scale of gravitational wave frequencies that they can study is about a hertz to a kilohertz, which are much lower than any kind of electromagnetic radiation. It's like megahertz, gigahertz. So it's very, very small frequency.
Sorry, I'm going to ask, what are the challenges in optical production from?
Well, the challenges are basically solving those differential equations. At this point, we've done it for sort of a very simple toy model of a matter field, which isn't a realistic matter field. But even so, what happened was my thesis student did this research, and we had this problem where things went to infinity, and we didn't when the waves were collinear. We didn't understand that, but he was able to do it in all the other regions, and he actually did an extension to, say, electrons or neutrinos. So it's not that hard to do the extension. It's just that I guess the big thing is that you've got all these huge equations, large number of terms. You could even see, well, I can't, but remember how big even the coefficients of that expression were huge. So it's really the difficulty is mostly to doing with being careful and solving those equations and dealing with very large expressions. Extending it to other real matter fields and electromagnetic is not really that different, other than it's going to add new terms and just make it bigger. Okay.
Did you end up solving those DEs numerically?
No, this was power series.
Oh, okay.
Power series. Generally, I haven't seen anybody approach it numerically. It's usually perturbation theory or power series.
That'd be a specific problem.
Yeah, I'm not sure. I haven't really thought about the numerical approach that much. It just seems pretty complicated for a numerical approach, but it's not to say it couldn't be done.
Any of the undergrads have questions? Dr. Fugleberg gets to grill you guys all the time, and you get a chance to ask him a question. No?
No.
Okay, no.
Kind of mentioned it in talk but the animation for the longer fine. Is that what's really going on in terms of to coming back in phase and then looking for a slight phase shift?
Yes. Yeah. But I'm not to say that, because I mean,
Really difficult to see something.
exactly. So I mean, I'm not an expert on that, but I would think that there's probably a lot more in the analysis than I presented here, and a lot more that I understand.
If you put that 180 degrees out of phase, so they cancel.
Yeah.
With no deviation, and then you get a deviation in the Y. Suddenly you see a little bit of light, you know, like a photon or something.
I guess the way I think about it is that if you were to detect, just measure the distance, like say, okay, I want to measure this distance for the lasers going just once. That would be really hard. But you're measuring it a lot of times a second, and you're looking for a pattern. And I would think that basically what you're doing there is you're building up statistics, because you're following a pattern, so you have something to go on.
Yeah.
And you're building up statistics. You're building up more and more data points that somehow can be sort of merged together, and then using all of those data points to tell you, oh, that's what this distance is.
And the semi drives by.
Oh yeah, I mean, when I say there have been 90 likely cases, that basically likely cases means greater than 50% astrophysical source. So they have a lot of detection, you know, a lot of sort of cuts that say, oh no, that can't be astrophysical. That has to be a semi going by, or that has to be something happening. I mean, one of the factors that you have these 4 different sites that, you know, all over the world. If you see it in Italy and you see it in Washington State, then that wasn't semi driving by Washington State, right? That was that because you saw it in Italy too, and
Yeah.
But yeah, I mean, when is, when I say likely sources, they're saying greater than 50% probability that it's astrophysical and not just something that happened in the atmosphere or some tremor.
Do they have to constantly be measuring, like to get it? They have to both be exactly 4 kilometers, right?
No, that's the thing though, because if I don't think they have to be, as long as you know, if they're in phase. And then they start to change, right? So you're looking for changes. So I don't know, I could be wrong, but I doubt that they can measure that 4 kilometers.
That's what I was wondering.
Yeah, I don't think they've actually measured that distance to better than, the a millionth of width of a proton. But if you're looking for changes, that's the important thing.
You're gonna be more insight in as to why the effect is collinear.
Well, that's what basically what I found in our analysis is that we found that there was a different behavior in the collinear direction. And there was a resonance feature in the terms of if you had a gravitational wave and a matter wave that basically had, well, the gravitational wave, one complete cycle, it does 2 oscillations. So if you had a matter wave that was twice the frequency of the gravitational wave, you'd have a resonance effect. The problem with that though is that there are no physical waves in the universe that have the frequency as small as gravitation. So if you ever to find a matter wave that has twice the frequency, then you'd be doing good. But unfortunately, that's not likely to happen.
Silly question. When you think about the expansion of the universe, expanding, space is expanding, but we're not expanding, we're held together by rigid bodies. So would it be the same with the LIGO part? Those 2 mirrors are not getting further apart.
The distance between them is increasing.
But the
They're
space between them is changing.
Yeah, the space between them is changing. But that means that the space between the atoms in your body is getting bigger too. So it is affecting you. But that's, again, when I had that ring that was stretching and expanding, or the cylinder, that's neglecting any possibility of rigid force with holding things together. So yeah, so I mean, you would have to take into account the effect on a solid body, but it does. I mean, one of the original ways of trying to inject gravitational waves was looking for the expansion of a big metal cylinder. So it does stretch the thing. It does stretch solid objects, but probably not as much because you're neglecting the internal forces in the thing. Because they gave up on that a long time ago when they came up with
The expansion of the universe, is that stretching galaxies? I'm saying.
But these are local, right? These are like stretching here.
Sure,
Yeah.
But
yeah,
it's an effect of expanding space.
Yeah, it is, but it's 10 to the minus 21, so you'll never see it.
Well, yeah, for the expansion of the universe, things are getting bigger.
Yeah.
Okay. What else? Nothing online. Okay, very interesting. Thank you very much. Once more, thank Dr. Fugleberg.